Hello class, I hope you're having a wonderful day. Today I would like to work through a practice problem that is covering motion in 2 dimensions. So what I would like to do is read the problem to you, and then I'm going to underline some important information. Then we need to generate a column of knowns and unknowns and draw a picture to help us solve the problem. So let's go ahead and get started. You throw a rock horizontally at 11 meters per second from a cliff at a height of 64 meters to the valley below. How far from the base of the cliff does the rock land? And we are going to ignore aerodynamic drag. So let's start to gather some knowns and unknowns, and then we're going to draw a picture. So our initial velocity in the x direction, it says that we throw the rock horizontally. So initial velocity in the x direction is 11 meters per second. And since we're throwing it horizontally, that means initially in the y direction, v sub I sub y, our initial velocity is 0 meters per second in the y direction, okay? Now we know that the rock is going to accelerate in a negative y direction due to the acceleration of gravity. So acceleration due to gravity identified by lowercase g, negative 9.8 meters per second squared. Okay, the height of the cliff is 64 meters, and this is going to be the final displacement in the y direction. Remember that displacement is a vector, and we know that the rock is going to fall 64 meters. So our displacement is negative 64 meters. And it wants to know how far from the base of the cliff the rock lands. So this is going to be the final displacement in the x direction. Okay? So this is what we're going to calculate. Let's go ahead and draw a picture here. So let's say you are on top of this cliff here, and you throw a rock with an initial velocity in the x direction of 11 meters per second. It's going to land there, and the problem is asking us to calculate the final displacement in the x direction, okay? And we know that this is 64 meters, and this is the final displacement in the y direction. Okay? All right, so the first thing we need to do is calculate the final velocity in the y direction in order to calculate the time that the rock is in the air. So since the rock is going to accelerate in a negative y direction, when we draw our vectors, so velocity in the x direction is 11 meters per second. We now have velocity in the y direction. Well, since we're ignoring aerodynamic drag, we're going to have a constant velocity in the x direction. So our x component will always be 11 meters per second, okay? But in the y direction, we have acceleration due to gravity in the negative y direction, so this vector will become larger. So what let's do is calculate the final velocity in the y direction. We're going to use the base equation. V sub f sub y squared is equal to initial velocity in the y direction squared plus 2 times acceleration times our displacement. Now what I'm going to do is I'm going to take our base equation here and adapt it to our situation. So we have final velocity in the y direction squared is equal to initial velocity in the y direction squared plus 2 times our acceleration, and we've already identified that the acceleration that the rock experiences is the acceleration due to gravity. So lowercase g times d sub f sub y. So our final displacement in the y direction. Now, we know that our initial velocity in the y direction is 0. So we can go ahead and get rid of this. This guy goes to 0. We have final velocity in the y direction squared is equal to 2 times negative 9.8 meters per second squared, multiplied by our displacement in the y direction, which is a negative 64 meters, because the rock falls down. And remember, this is displacement, so it is a vector. Okay, so let's go ahead and take out our calculator. So 2 times negative 9.8 meters per second squared, that's negative 19.6. We're going to multiply that by negative 64, and we get 1,254.4 meters squared per second squared. So we have meters per second squared times meter. Algebraically, we can write that as meters over 1. So meters times meters gives us meters squared. Now, we're not finished here because we have final velocity in the y direction squared. We need to eliminate our squared. So we're going to take the square root. And what you do to one side to keep it balanced, you have to do to the other side. So we're going to take the square root of both sides. So on your calculator, the square root of 1,254.4 is 35.42. Not only are we taking the square root of the numerical value, we are also taking the square root of the unit value. So the square root of meters squared per second squared is meters per second. Okay? Now, we need this value to calculate our time interval. But we're not finished here because, remember, velocity is a vector, so we have to include the direction. And we know that in the y direction, the velocity is pointing down. The velocity vector points down. So what we can do is we can put a negative sign on this to show direction, or we can write down, or negative y direction. Anything that shows direction is okay, but I like to put the negative sign there. Okay? So I'm going to erase this to free up some room, but I'm going to write our final velocity in the y direction over here. Negative 35.42 meters per second. Okay, as I mentioned earlier, now we have to calculate the time that the rock is in the air. So what we're going to do is use the base equation. The acceleration of an object is equal to the object's change in velocity divided by the time. Okay, so this is going to be the final velocity in the y direction minus the initial velocity in the y direction divided by delta t, and I'm going to use a subscript here of hg, and that means to hit the ground. So the moment you release it, we need how long it's going to take to hit the ground. Right as you release it, how long does it take for the rock to hit the ground? And so that is what my subscript here, hg, represents. So what I'm going to do is I'm going to isolate the time to hit the ground by multiplying by delta t sub hg, and then on both sides of the equal sign, and then I'm going to divide by the acceleration. Okay? So what we have here is the time to hit the ground is equal to the final velocity in the y direction minus the initial velocity in the y direction divided by the object's acceleration. Now, I want to be a little bit more specific here than a bar. I want to put the variable g here because we know that the rock is accelerating towards the surface of the earth at the acceleration due to gravity, negative 9.8 meters per second squared. So there we go, right there. So the final velocity in the y direction, we already calculated that. That is negative 35.42 meters per second. The initial velocity in the y direction is 0 meters per second. And we're dividing by negative 9.8 meters per second squared, the acceleration due to gravity. So on your calculator, 35.42 divided by negative 9.8, we get 3.614. And we have units of seconds here. And let's talk about units really quick. So in my numerator, I have meters per second. In my denominator, we have meters per second squared. Remember, when we divide fractions, it's like multiplying by the inverse of the denominator. So what I have is meters per second times the inverse of our denominator. So the inverse of meters per second squared is going to be seconds squared per meter. Okay, so we can see here that the units of meters will cancel and one of our seconds will cancel. So meters are gone, one of the seconds are gone, and this leaves us with units of seconds. So 3.614 seconds. Now remember that we are ignoring aerodynamic drag. So we are going to have a constant velocity in the x direction. So what we can do here is say the final displacement in the x direction is equal to v bar, the average velocity, which is just, we have a constant velocity of 11 meters per second in the x direction. So to be specific, I'm going to put a subscript of x here, and then multiply it by the time to hit the ground, okay? So we have constant velocity in the x direction, 11 meters per second. We're going to multiply that by the time to hit the ground, 3.614 seconds. So we have 39.75 meters. And right here we have meters because our units, before we took the product of these two values, have meters per second and seconds. And this can be written as seconds over 1. So our seconds will cancel, leaving us with units of meters. Okay? So the displacement in the x direction from the edge of the cliff is 39.75 meters. So I hope this video has helped you with the first problem on the packet. If you need any more help, please give me a call, or you can send me an email or a message on Canvas. I hope you have a wonderful day.